This is a test run on my nuclear capstone oral presentation, The Past, Present, and Future of Thorium-Based Reactors. My presentation will discuss the possibility of using thorium as a fuel in nuclear power, specifically the LFTR, the liquid fluoride thorium reactor. This discussion will cover the need for nuclear power, the history of nuclear power, the evolution of the LFTR, advantages and disadvantages of the LFTR, previous nuclear power accidents, and if there is a future for LFTRs. The first topic that I'm going to cover is energy needs. The world needs nuclear power. Currently, we have 435 commercial power plants operating in more than 31 countries, creating over 375,000 megawatts of electricity. 11% of the world's electricity comes from nuclear power. Hopefully, at the end of this presentation, we'll have a new way to make even more. The two fuel types that we will discuss are uranium, which is the leader in today's market for pressurized water reactors and boiling water reactors, and thorium, who could possibly be the leader of tomorrow with the LFTR. Early reactor designs were based on and created from research from the Manhattan Project. Nuclear power research was basically to make a bomb. Over the years, research, and after the war was over, research focused on creating electricity. The main research facility was at Oak Ridge National Laboratory, which the eventual director, Alvin Weinberg, created a couple of experiments that we will discuss. In the beginning, they had to think of different reactor designs where they would have to decide between using a breeder type reactor, a non-breeder type reactor, if you want to use fast neutrons, thermal neutrons, what type of coolant you want to use, what type of moderator you want to use, if you even want to have a moderator, what type of fissile material you can use, uranium-235, uranium-233, plutonium-239. All of these ideas were discussed and hashed out over the years at the Oak Ridge National Laboratory. After the war was over, the next phase for the Oak Ridge National Laboratory focused on creating reactors for naval propulsion. Admiral Rickover, at the time was Captain Rickover, when he was studying at the Oak Ridge National Laboratory, wanted a submarine that could stay underwater for a long period of time. Not only that it could stay underwater for a long period of time, but that could travel as fast underwater as it could on the surface. Eventually, Alvin Weinberg convinced Rickover that the pressurized water reactor was the best type of reactor for a nuclear submarine. Alvin Weinberg summarized it as, it's a compact, simple reactor that would be perfect for a naval submarine. With the pressurized water reactor being the lead reactor developed for the nuclear submarines, it had major advantages over the other reactor designs of the day. It had extensive research, it was used in nuclear submarines, so naturally it led to civilian power plants being created. Today in the United States, we have 99 commercial powered reactors. 65 are pressurized water reactors, 34 are boiling water reactors. They're solid fuel rods, uranium-based, and light water. An alternative to the uranium-based reactor is a thorium-based reactor. Alvin Weinberg performed extensive research on thorium reactors also while he was at Oak Ridge National Laboratory. And in fact, even though he was one of the leading factors into using the pressurized water reactor for naval propulsion, he eventually went away from the idea and thought that a thermal molten salt reactor would be the best option. The idea came from originally designing a thermal breeder reactor. Thermal breeder meaning more fissile atoms are created than are destroyed. His first reactor that led him to the path of the molten salt reactor experiment was the homogeneous reactor experiment, which on February 1953 was created and lasted approximately 1,000 hours. They shut it down because they had no way of maintaining the reactor. It was not designed to be extended for a long operating time and did not have any way of performing maintenance on the reactor. The second was the HRE-2. This was developed in 1958. It operated for 105 days continuously, 220 total, but had some major problems. In fact, the core was made of zirconium and actually melted through, and they had to perform repairs to get it going again. They were successfully able to engineer the core, get it running again, and then again the core melted out. That was eventually shut down, that project, and a new project was developed with a new designed core, and this was the molten salt reactor experiment. The molten salt reactor used salt combination to create a liquid fuel. It was a thermal reactor and it was a breeder reactor. It operated approximately 4 years during the 60s, from 1966 to 1969. The molten salt reactor had three major advantages. One, the molten salt was more compatible with stainless steel to create the core. Two, and maybe the largest advantage, it could operate at atmospheric pressure. And this was the first one that combined thorium and uranium into the dissolved salts, which we'll get into the advantages of that later. The molten salt reactor operated for 4 years and was eventually shut down in 1969 because it lost its funding from the US government. Alvin Weinberg was especially upset. He thought this could be the future of reactors. Unfortunately, he never got the chance to continue. Which leads to today's thought on the liquid fluoride thorium reactor. It's an improvement upon his molten salt reactor experiment. The liquid fluoride thorium reactor's main components is it has a core with two fluids. The core will have uranium-233 surrounded by a blanket of thorium-232. It would have a uranium separator, a waste separator, and a heat exchanger to create the electricity. The LFTR operation is the uranium-233 in the core is fissile material, create a chain reaction, and it is in a molten salt which is a mixture of fluorides of beryllium and lithium, a term that you now will hear on the internet described as FLIBE. When that chain reaction occurs, it heats up the molten salt. That molten salt is then carried away from the core and into the heat exchanger, where there's a separate containment, like a primary and a secondary containment, that has clean salt, which that molten salt will heat up that secondary salt, and then that heat from the secondary salt is then turned into steam for electricity. In addition, some of the neutrons that escape from the core of the uranium-233 will be absorbed by the blanket thorium-232 and decay into uranium-233. This is the breeder aspect of it. That is then separated out by the uranium separator, and the uranium-233 is then funneled back into the core, and the cycle starts again. The advantages of the LFTR are, number one, I said that it can operate at atmospheric pressure. That will reduce the cost of design. It's also a safer operation, safety for the staff. You're not going to have any steam leaks. The stability of the reactor, it's more stable. It can basically operate itself. It doesn't need control rods. The liquid core versus the molten core, so it can't melt. It's already at a liquid state. It has a inherent safety feature with the freeze plug. Basically, the freeze plug is like a drain on the molten salt. So the freeze plug needs energy, electricity, to keep the plug frozen. If electricity, for any reason, a failure, is taken away from the reactor, then the freeze plug will melt and drain the molten salt into a container, so there's no radioactive accidents. Also, thorium is more abundant than uranium. It's 4 times more abundant than uranium, and 5 times more abundant if you compare it to uranium-235. And according to Dr. Hargraves, who wrote the book Thorium, Energy Cheaper Than Coal, Dr. Hargraves states that the LFTR will produce 1% of long-lived radioactive waste compared to the light water reactors. Of course, the LFTR also has some disadvantages, according to some major disadvantages. One disadvantage is the continuous process of removing the poisoning products from the fuel. It's going to require some additional engineering that was never perfected. It was able to prove that it could be done, but never on a large scale. Also, the LFTR will have a buildup of noble metals in the core, which could be dangerous depending upon where they build up. The main concern also is that you have molten salt, so you're going to get a lot of corrosion, and you're going to have to figure out the components that can deal with the radiation damage and not deteriorate. Also, you're going to have graphite swelling and what they call a plumbing problem with the two salts and keeping the uranium and the thorium, keeping track of where the uranium is in the core, and preventing leaks. To summarize up the disadvantages, really it comes down to research and development. The project was defunded in 1969. The ideas that they operated from need to be improved and need to be performed on a large scale. It only has 4 years of operation, and that was the molten salt reactor experiment, which the LFTR is actually an improvement on that design. So this would require, again, more research, more development, which costs a lot of money. It's going to cost time, and there's a lot of unknown that needs to be figured out and needs to be approved from different regulation committees, the NRC, the public backlash. So it has some major hurdles, but it also has some advantages. And the point of this is, should we research it? Right now, the public has a fear of nuclear power, the majority, mostly because uninformed decision, but some that are against it know exactly how it works. And 2 major nuclear events that lead to the public fear of nuclear power were Chernobyl and Fukushima. 3 Mile Island as well, but another team is going to discuss 3 Mile Island, so I'll leave that to their expertise. So I want to discuss the 2 events very briefly and see if the LFTR would in fact prevent this sort of disaster from occurring, which would be excellent news for the public and for public backing and government funding. First off, the Chernobyl was a type of pressurized water reactor, but it wasn't the same that we use in the United States. It was actually an RBMK design. The control rod design was different, which actually led to the accident. It certainly helped increase the radioactivity. The tips were radioactive, and when they were inserted on the scram, they actually increased radioactivity even more. And maybe the most dangerous aspect of it, it had a positive void coefficient. As steam bubbles increased, the radioactivity increased. The staff was poorly trained. They were a poor design, and they tried to run some safety tests by removing the safety features that it had, which led to the accident. For this research, I would say that both the United States pressure water reactor and the LFTR, both designs could have prevented what happened in Chernobyl. There was a lot of circumstances other than reactor design that led to that failure. So I don't see an advantage of the LFTR over the PWR in that. I think the United States could have easily operated and that could have been avoided. As for Fukushima, it's a little different. The Fukushima is a boiling water reactor. They had an earthquake, which caused a scram, which caused a loss of power, which caused a loss of their coolant, and immediately they went to their backup diesel generators, which unfortunately the earthquake caused a tsunami, which also took out the backup diesel generators. Eventually, to summarize it up, the cores, which were liquid fuel, wound up melting down. There was hydrogen explosions. And I think the LFTR could have helped in this aspect because the core was liquid core, and in a cost of a earthquake and a tsunami and a loss of backup power and a loss of diesel generators, the freeze plug would have activated, it would have unfroze, and the liquid core would have drained to a storage containment, and it would have been sealed. And I think we could have avoided the issue with Fukushima. Because of the aspect of the liquid core and the other advantages of it operating at atmospheric pressure, I think that it's a possibility that the LFTR could solve some of our future energy needs. In fact, as we speak, China is investing heavily into LFTRs, and they are looking to go online with LFTRs by approximately 2020. India is also performing research into thorium reactors, although they're not using the LFTR. They are going to use a different type of thorium-based reactor with heavy water. And India, which currently uses about 4% of their electricity from nuclear power, expects by 2025 to have 25% of their energy from nuclear reactors, specifically thorium nuclear reactors. In conclusion, the LFTR is a thought. The LFTR is an improvement on the molten salt reactor experience performed by Alvin Weinberg in the late 60s. It will take considerable research and development to have an LFTR operate. But LFTRs could help solve the world's energy problems and could help operate in countries where they have energy needs. It's a clean energy, it's a safe energy, and it's a breeder, so it'll keep creating the fuel. We won't be burning up the uranium. My final thought is that the US government should reinvest into the LFTR, open up a research facility similar to the Oak Ridge National Laboratory, and develop our own liquid fluoride thorium reactor.